Today class on continuous distribution. So this is on continuous distribution. What we discussed earlier? We discussed earlier first some probability, and before that we discussed on this what is sample space, what is random variable, what is event space, then probability and random variable. So important part is probability and another part is random variables. So these are important concept. Obviously, probability and random variable has under the same structure. The structure is called probability space. There is a sample space, say S or omega. Obviously, is non-empty. Is actually the outcome of all outcome of a random experiment, like coin toss or throw a die. So all outcomes are called set of all outcomes are called sample space. And there is a sigma algebra. If it is a finite sample space, we take the sigma algebra as the power set. But if it's infinite or uncountable, sometimes we take it's a special type of sigma algebra. Like in over R, we take Borel sigma algebra. But in our situation, for the discrete case, we take the power set. So if we take the power set, the situation will be very simple. Otherwise, if you take a general sigma algebra, then it will be slightly complicated. Sometimes it's very complicated. Now, there is event space, the sample space, then event space. The events are set of event space is set of events, and events are subset of this sample space. May not be the all subset, some subset. For power set is all subset. And then we construct a probability on this event space and a random variable on this sample space. Now, what is random variable? And its outcome is a real. Sometimes random variable is a real value random variable. So outcome is a real value. So it's like a random variable. If you take x, so x of h is a 1 and x of tail is a 0. And another the side of the coin is that is a probability. One side is random variable, other side of the coin is probability. Probability defines on the event. So once it defines on the probability event, so it's like an event space. So it's a omega is a sample space and it's a real line. So it's actually on 0 to 1. So now there is a random variable here to R. So this is R. So actually R is a line, but we take just like a Venn diagram. This is a real set of real number. So actually we represent the set of real numbers in a line, and this is 0 to 1. This line segment. And there's two functions like that. So one function is actually every element of this go to this element, but here the probability function is not defined on the omega. It is defined on a subset. So some subset A. So it's a probability of A. The probability of A is here, somewhere here, and this x omega is somewhere here. So remember, omega is a point, is an outcome, like a head, and A is a subset, like a set containing head. And this probability is not on the head. The probability of truly speaking, its probability of head is meaningless. The probability of set containing head, and x of head is a real number. So then what we do, we take a subset here. So it's also called Borel set, the special type of subset, and you take the pre-image of that. We go to the back side, so it is x inverse b. So x inverse b is a subset of omega, and not only the subset of omega, it should be such a x must be such a random variable. It's also a measurable function, such that this is belongs to the script type. This must be event. It must be event. So that type of set, which now since it is an event, we can talk about the probability. So we can talk about the probability of that. So just remember the structure. What is the structure? There are three different things. One thing, in a real number, there is a set, subset. Say is a intervals, or maybe finite set, or maybe count rational number, set of irrational numbers, something like that. Some is a Borel set. One thing is this is B. This is subset of R. Now, If you take x inverse b, what is x inverse b? What is the definition of x inverse b? Definition of x inverse b, the set of all omega in omega. So now it is omega is a sample space. So it's like a head. If it's tossed thrice, like it's a head, tail, something like that. And this omega like head, tail. And this says that this x omega is belongs to that b. Now this is the definition of x inverse b. So this is a subset of omega because you take the collect the elements from the omega. Now this x must be such a function such that this x inverse b must be an event. Obviously, it is a subset, and this sigma algebra is power set. Then is no problem. Every subset is an element of power set. But if the sigma algebra, the event space, is not the whole power set, then we have to very careful about to choose x as that this x inverse b must be a event. Otherwise, we can't talk about the probability of the event. So it is a probability of the not the probability of the b. It is probability of x inverse b, because probability defined on the subset of omega, not the subset of R. And this is actually the composition function, like x p inverse of this. And also this is right as p probability of b set, but is induced by x. It's like a probability of b, but this probability is not that probability we define in the sample space or over the event space. This is a px, and this is called distribution. This px is known as distribution. This px is known as px is called distribution of x induced by the probability function p. So two things is there. So one is random variable and another is the probability thing. If we change the random variable, the distribution will change. If we change the probability thing, then also the same random variable, since the probability is changing, so this distribution will change. So what is distribution function? Distribution function, something like that, is a function from real number to 0, 1. So it is again it's a probability. So it's 0, 1. Now f of x for all real x, f of x we define like that. We by definition. So by definition, this colon means by definition the probability of x less than equal to x. But what is the meaning of probability x less than equal to x? Whether x less than equal to x is even. Okay, x is a function. So how can a function is less than some number? Actually, the thing is not the x are not x. The function is not the less than x. Actually, the output of the function is less than x. So it's actually x omega which is less than x. And we collect all that omega. We collect such omega such that x omega is less than x. And we are talking about the probability of this event. So x less than x, capital X is the random variable, small x is the real number. So capital X is the function. Now this is x less than x means this set, and this is actually the set x inverse, the intervals minus infinity to x closed. So this interval actually the set of all y in real numbers such that y less than equal to x, and x inverse is this. So this why these two are equal. So we can define the definition of that. So what is the definition of this? So this by definition this is actually okay. We should actually write one more bracket. So this is the set B. This is the in subset of real number. So we should take one more bracket. So what is this? Is a set of all omega in omega is by definition such that x omega belongs to this set. But what do you mean by something is belongs to this set minus infinity to x? That means actually there's means x omega less than or equal to x. So we take the probability of that x inverse the b. The b is here minus infinity to x closed interval. So this is a probable set. This is an interval. So we can talk about the inverse of that, and inverse of this is a event. So we can talk about the probability. Okay, but is this sufficient to check all this Borel set, the probability of all this Borel set? Is it true? The question is, say if I take any other set, say not like the interval. So you say something like say interval from 1 to say 3. Can I write we take this inverse of that, and then we want to consider this the probability of this thing. So sometimes we write in this notation. So 1 less than x less than equal to 3. This 1 less than x less than equal to 3 means is not x less than equal to 3. X is a function. How can a function be a less than 3? The output of the functions are less than 3. So we have to such an input. We have to collect all such input that output is less than or equal to 3 and strictly greater than 1. That means is actually set of all omega in omega in the sample space. This outcome small omega of the outcome such that x omega is strictly greater than 1 and less than or equal to 3. So we want to find the probability of this whole set. Now, how can I write this this probability in terms of this the distribution function? We can easily write, because this set is nothing but is a set like omega belongs to omega such that x omega less than equal to 3 minus the set omega belongs to omega such that x omega less than equal to 1. So if you take the element of this set less than strictly less than equal to 3 minus the less than equal to 1, that means it is from 1 to 3 and strictly greater than 1. Now this we know this probability of A. What is this probability of A minus B? Probability of A minus B is probability of A minus probability of A intersection B. This is the result on probability. But here, what is A? Say it is A set. Now this is a B set. What is the A intersection B? A intersection B is actually B. So this is probability of A minus probability of B. So A intersection B is just B, because B is a subset of A. Once it is less than or equal to 3, it must be less than or equal to 3. Once it is less than or equal to 1, it must be less than or equal to 3. So any element B in B belongs to A. So B is a subset of A. So A intersection B is B. So this is actually probability of A minus probability of B. But what is probability of A? Probability of A is just this thing. So it is f of 3 minus f of 1. So we can easily find that the probability of this such an interval, finite interval, using this minus infinity to x. So this is called distribution function. So that's why distribution function is very important. You can write every Borel set, subset of real number, and probability of that in terms of this fx only. I'm not going to details in this. I just give some examples. Say, take your set is like that. Say, take your set is like 1 to 3 union, say 5 to 7 or 9, like that. And we want to find this probability of this set. By the way, again, what is the meaning? Meaning is set of all omega such that x omega belongs to that. Once I write x belongs to B, that means set of all small omega so that x omega belongs to B. It's just simpler notation to write some set. So again, what is this? Again, this two are union is disjoint union. So we can write this like a probability belongs to 1 to 3, and then plus probability of, because it's a disjoint, 5 to 9. And now what is 1 to 3? It is f of 3 minus f of 1 plus f of 9 minus f of 5. So we can write in terms of this f function only. Now we can talk about what is the then probability of x equal to, say, 3. How can we write that? Just a single element. Is it f3? f3 minus f3? Is it 0? No. F3 minus f3 just it will be 5 sets, so 0. But it is not that. So how can we write? This is slightly complicated. How can you write x equal to 3 in terms of that type of intervals? So this is slightly tough. So we have to take like this. So we have to take this type of set, and we have to take the union. Then we can find the probability of this, and we have to take the union of this thing, and this set is actually 1 to 3. Now, and we can find the probability of this set. Oh, sorry, x belongs to this. Sorry. That we can find in terms of the capital F. That we can find in terms of capital F. And so this is union. So we can find the probability of this using this F. We can write this in terms of f. So it is f of 3 minus 1 by n minus f of 1. And with those, from that we can write the probability of x belongs to 1 to 3. And that takes a limit, because it's a in n equal to 1 to infinity is contains its required limit. So I just not going details in this limiting sense, limit of a set. And once I find the probability of this, we can easily find the probability of x equal to 3 is nothing but is the probability of x less than x belongs to 1 to 3, that we can find using f of fx, f3 minus f1 minus this. It is actually x equal to 3. So I'm not going to details in this because it's required limit and some real analysis thing. So, but just is to for your information, you just you can write every like one singleton element probability in terms of that only this type of set only. So you can write any Borel set or any singleton or any finite set or any closed or open interval in terms of only this type of interval using just complement or union. It may be the infinite union. So we can write we can find any probability using that f function. That's why this f function, the distribution function, f is called the distribution function. Distribution function of x, or sometimes we write f suffix x. Sometimes we write f suffix x to say that this function is coming from the random variable x. So if you change this random variable to y, then it will be fy. So not the same f, capital F, it will be f of x, then f of y, something distribution function. Sometimes we write f for x and y, g for y, but this is slightly problematic, because if you have a say 3 or 4 many random variables x, y, z, then how do you write f is the distribution function of a x, g is the function of distribution function of y, and then k is the distribution function of z? It's slightly complicated. Better to say the random variables are x1, x2, dot, 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 say x5 or x10, and the corresponding distribution is f of x1, f of x2, f of x3, or you can write just f1, f2, f3, f10. That will be a better notation. So that's why we sometimes write fx, or we just write f if there is only one distribution function. But remember, this f depends on the random variable x, and obviously that depends on the probability also. So distribution function is actually generated from the two different things. One is random variable, and this is the probability. So in distribution function, they are clubbing. The random variable concept and the probability concept, they are both clubbed, both merged in a single concept, which is called distribution function. Now, what will be the properties of the distribution function? The important properties of the distribution function is, number one, it must be lies between fx must be lies between 0 to 1. So because it is a probability, we just write say f instead of fx, and then f must be increasing function. It is an increasing function. We write this notation, increasing function. It will be greater than or equal to 0, less than or equal to 1, and it is increasing, and the limit x tends to infinity, this fx must be 1, because as you take the whole set, it will be 1, and limit x tends to minus infinity, it is going to phi that, so it will be 0. And the last one is very important. This f is right continuous. Limit x tends to y plus fx is y. So it is called right continuous. So what will be the graph of this distribution function? Take one, or consider a concrete example. So take an example of discrete case. Say very simple case. Say x is a Bernoulli. X follows Bernoulli. Say Bernoulli. Say what? Say 0.3. That means probability of x equal to 1. So head here, x equal to 1 means head, x equal to 0 means tail. The Bernoulli distribution is 0.3, and probability of x equal to 0 is 0.7, and otherwise it is 0. So x equal to x. It is 0 for all x not equal to, not does not belongs to 0 or 1. Now, what will be this function, this f? Now it is clear that once I in the below 0, if I take some x which is less than 0, this would be 0. Because if you take f of minus 1, that means the probability of x less than or equal to minus 1. And x less than or equal to minus 1 is nothing is there. So it is just 0. But if we take x equal to 0, what happens? X equal to 0. That means f of 0. What is the definition of f of 0? It is just probability of x less than or equal to 0. But what is x less than or equal to 0? Is only one point, the tail. And that probability is 0.7. Again, if we take distribution function of 0.3 or 0.397, this again it is probability of x less than or equal to 0.397, but again it is just probability of x equal to 1, x equal to 0, because only x equal to 0 and x equal to 1 has the positive probability. So that means this 0.7 will be occur up to 0.1, but when you have probability of 1, it is just x less than or equal to 1, that means the whole set, so it is 1. And if you take again, if we take f of 1.32 like that, it is again 1. So for x greater than or equal to 1. So what will be the graph of this function? So graph like that, if we just plot this x and here fx, if we plot that, and this graph will be like that. So up to 0, it is 0. So this 0.3 here, and then this, and it is 1, and this is up to 1, and this is 0.3, and now this is. Now, since it is a discrete type random variable, we always have this type of distribution function. For discrete type is always, it's also called step function like that. This first time somewhere it is 0, then here to here something is say this, up to that, and then again something like that, and then it goes to this 1. So it is like a discrete type, and obviously the finite, not only discrete, is finite, because only 3 points are there where is a jump, discontinuity, and these 3 points have the positive probability, and other point the probability is 0 because they're flat. The step function. It's like a the whole thing, whole mass concentrated on the 3 points. The whole mass in the real line, the total mass is the 1. The probability is also called probability mass. So probability mass, the total probability mass is 1, and I put them in 3 different points. Say it is 0, say it is 2, and say it is a -1. We put -1 and 2 here, and we put some masses here. So what is the mass here? Say if it is a say 0.3, then we put mass 0.3 in -1. Say if it is a point, say again 0.3, we put a mass 0.3 here, and if it is a 0.4, it must be 0.4. So we put a 0.4 here, slightly bigger mass. That means whole mass you just break into 3 parts and you put some 3 points. It may be the finitely many points. It may be the uniform, like uniformly random. What is uniformly random? So uniformly random means x can take only values. The spectrum of x is called the spectrum of x. It takes only values say 1, 2, 3 up to say n. N is a natural number, say 100 or 200 or maybe 5. And what is the probability? Probability of x equal to x is just 1 by n. Same probability, each have the same equal probability for x belongs to this set. And if x does not belong to that set, so if x is a -1, probability of x equal to -1 or probability of x equal to 2.3, then it is 0. So this is again a finite thing and is equal probability. It may not be equal. Say probability of x equal to 1, say 0.01, then x equal to 2 is say 0.02, or x equal to 3 is say 0.15, like that. But every positive probability will be positive, and the sum must be 1. It can't be less than or greater than 1. So this is the thing. So this is the idea, and it may be an infinite thing. So infinite, it is discrete but infinite, like Poisson distribution. So what is Poisson distribution? if the Poisson distribution is like that, x follows Poisson, lambda means we see that probability of x equal to small x, and small x can take only 0, 1, 2 non-negative integers. This is e to the power minus lambda lambda to the power x by x factorial, and otherwise it is 0. If you x not in the 0, 1, 2 dot 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 dot, it is actually 0. Now this is infinite thing. So here the graph is something like that. So here up to 0 it is some 0, and then it is jump there, and then up to 1, then up to 2, then up to 3. This is the bounded by the 1, and it can't go beyond 1, but always less than 1. And but this is slightly this something like that. It's like asymptotic thing, must never touch 1. So this is infinite but discrete. What is the idea? Idea again is same. If you have a total mass 1 and you put the masses in non-negative integers with this, but total mass is 1. So we put here say something, we put here smaller or some bigger or maybe smaller. You should have to smaller mass because otherwise sum cannot be 1. Something like you put half in 0, 1/4 in, that is not the Poisson distribution, that is geometric distribution. Half in 1, so probability of x equal to or probability of x equal to 0 is half, say, or probability of x equal to 1 is say 1/4, probability of x equal to 2 is 1 by 8, probability of x equal to 3 is 1 by 16, and this total sum is 1, even though the high infinite GP sum is 1. So this is also a distribution, something like probability of x equal to n, where n is belongs to 0, 1, 2 dot 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 dot. This is just 2 to the 1 by 2 to the power n plus 1, and this sum will be 1, infinite GP. You know that is infinite GP sum is 1, so half plus 1 by 2 square plus 1 by 2 cube, this sum infinite sum is 1. So it is an infinite distribution but discrete. But the basic idea for the continuous distribution is like that. So now consider a rod with total mass 1. And if I ask what is the mass of a point, single point, the answer is 0. The mass of a single point is 0 because the volume is 0. The volume of a point is 0. So at every point, the mass is 0. Then the question how the total mass is 1. The same question like what is the length of a point? The length of a point is 0. But a line consists of infinitely many points. So how infinitely many 0 add up to the 1? This is a very basic question on this called measure theory. I will not go details on that. The question is if it is every point is a mass 0, then how this total mass is 1 or maybe some finite mass. So there is no question of mass at every point, but somewhere maybe this is some higher density, here maybe some lighter thing, maybe here is some dense. So now this is a concept of density. So it is a in density is the concept in the continuous version, not in the discrete version. Discrete version, every point has some mass. So there are finitely many points or maybe infinitely but discrete. 1 at some 1, some value is there, 0, some value is there, 2, some value is there. In between 0 and 1, everything is 0. So it is called discrete, it may be finite, it may be infinite. If it is infinite, it should be countable. Now this is different thing. This is a continuous, and every point the probability is 0. So like every point of the mass, every point of the rod, the mass is 0. So, but we know also if for is iron, this is a heavier mass, for it is a wood, that may be a lesser density. So in probability distribution also something, same thing. In somewhere it may be the higher probability, in somewhere is the lower. Like that, if you take some slight of this total mass here, if it is the same length, this mass will be less than that part. That means this is a higher density than this. So then we have to take a density function, and the density function like a graph, say this is a density graph, And what is the mean density graph? So it is x and is a density. Sometimes we call it a small f. That means this around say 0, the higher density. And how do you, and every point that area is 0, you know. And if we take slightly here, say if you take from here to here, say from 3 to 4, how do you find the mass between the 3 to 4? You know, this mass between the 3 to 4 is just the area under the curve. So it is just an integration. So integration density is actually give the mass, because the density is derivative of the mass. If m is the mass and x is the length, so or a is the v is the volume, then dm dv is actually the density rho. And to find mass, you have to integrate that mass function with respect to the volume. And if you take the, it is every cross section of the same density. If we assume that a cross section is same density, along this cross section density is same, we just then the density is a single valued function with respect to say x. If we just count x here in this along this direction, is only one dimensional. Other two dimension is a fixed. Sometimes it's called density in per unit area. Cross-sectional density in physics, they call it cross-sectional density. So it is only one function, only one direction is changing, not the other x, y, z direction. So probability mass is something like similar idea. Is only one direction the probability is changing, because this only one direction is there, f of x. So x is in the real line, and here the same, say -1 to 0, the probability is higher because the area is higher, because the density is higher. So this is the idea of mass density function, like a density of a body. So correspond between the density of a body and mass of a body is same thing as the density function and the distribution function. In probability, the distribution function act like the mass, and this density function, probability density function, is act like the density of the physical density of a body. Similar concept in the mechanics also. In mechanics also, this mass is like the distance displacement covered, and the density like the velocity, but the velocity is higher, the distance covered is higher. So that's why velocity is the derivative of the distance covered, displacement, and displacement is the integration of this velocity. So this is the same idea. So that's why the small f is also called PDF, probability density function, and this capital F is called probability distribution function. It's also PDF, so that's why we write only DF. We don't write probability density function, we write just distribution function, DF, that means the capital F, and the small f, that is the density function, PDF. So what is small f? This is nothing but the derivative of this distribution function. And how can find your derivative, your distribution function from the mass the density function? You have to integrate from x to infinity, minus infinity to x, that f function, you should write y, the time variable, y dy dx. So capital F is the primitive of f, and this small f is the derivative of capital F. So it is, you know, this is the Riemann first theorem on fundamental theorem on integral calculus. That is the Riemann first fundamental theorem of integral calculus, that every function which is a this thing is a derivative, then with vice versa. The other one is the integration of this, assuming the continuity and everything is there. Some conditions are there. If it is not a continuous function or derivable or something not absolutely continuous, then this is not happen. But assuming that that condition is hold, then we have this. So this is the idea of the density function for the continuous version. Now, in the continuous function version or continuous random variable, we have one more concept than distribution function. It's a probability density function. And for the discrete version, two things is there. One, distribution function is always there. Whatever is a discrete, or is a finite, or infinite, or is a continuous, or is a mixed distribution also there. Random. Something is continuous, somewhere it is a discrete. Whatever may be, distribution function is always there, because the distribution function defined like probability of x less than or equal to x. But density function is not that. It is just a derivative of that. It requires some condition. And other way, for the discrete is called probability mass function. There is one called probability mass function, where this probability is positive. Where this probability is positive. That is called probability mass function. For which x this is positive, we say at that x, small x, the positive probability is there, positive mass is there. It is for the discrete version, and density for the continuous version. But whatever discrete or continuous are there, the capital of the distribution function is always there. So that is always there. So there's several type of continuous random variable. The most important continuous random variable is normal distributions. It is normal, say mu sigma square. Two parameters are there. If you change your mu and sigma square, then it will change. And the density function of this distribution is 1 by root 2 pi e to the power minus half sigma square x minus mu whole square. So it is for every x. So this is the density function. So at every point the probability is 0, but is a density function. So it is a density function. So what will be the distribution function? It's just the integration of that. So integration of minus infinity to x 1 by root 2 pi sigma e to the power 1 minus 2 sigma square y minus mu whole square d. Now the problem is you can't integrate this. This is a one sort of called incomplete beta function. Incomplete gamma function is actually improper integral. This is a beta gamma, it's a gamma function, incomplete. You can't integrate that. You can't integrate this. So you have to write in this way. So the question, how do you know what is the probability of say x less than or equal to say 7 or x less than or equal to say 3? So okay, we can't integrate that. So we can't use the calculus. We have to use the numerical thing. It's called numerical analysis. There is a several method to find this Gauss-Seidel method, Gauss-Jordan method. Numerical integration is the one way before computer age. But after computer age, there is a different method to find this integration. It's called simulation. Using simulation, you can using random number thing and using computer software programming, using simulation technique, you can easily find that this value. And this in every book there is a chart of that standard normal thing. There is a chart, and in chart we can find that if you can find that what is f of 3, f of 5 in the chart. In the book there is already everything is written there. But remember this, when this chart is prepared, the computer is not there. So they used just calculator or in hand they use that to find the charts. But nowadays this chart is actually useless because everywhere in computer or you can in Google you can search this. You can just say what is the value of this. Your Google will say this is the value of this. No need of actually programming. Everything is there in Google. So there is one more thing is the normal distribution, something we call standard normal. This is called standard normal. Sometimes we write U or Z, not U. U is for uniform. It's called standard normal. This is called standard normal variable, variable. So normal variable. Where mu is 0 and this sigma square is 1. And we let us see that this expectation of this, that x is actually mu. So here expectation of the standard normal distribution is 0. That's why we call standard. And variance of that x is sigma square, and so why the variance of z is just 1. So once any random variable variance is 1 and expectation is 0, we call the standardized random variable. It's called standardized random variable. Because mean is 0 and variance is 1. So it's a standardized normal variable. So it is called standard normal variable. So what is the distribution function? If it is standard normal, we don't write f, we write capital phi. Capital phi is fixed for the standard normal variable. If I write capital phi x, it is just assume that is coming from the standard normal variable. So it's just the integration of minus infinity to x small phi x. And what is small phi x? Small phi is the density function of the standard normal variable. So what is small phi? So it is 1 by root 2 root 2 pi, sigma square is 1, so e to the power minus half, sigma square is 1, and x square, mu is 0. Sorry, x is any real number. And what will be the graph of this function? The graph of this function is called bell-shaped function. Like a bell, the function is like that. Is peaked on this 0 and the symmetrical with respect to the x-axis, and it's never 0. It's a lower, but it can't be 0. Obviously, it should be positive everywhere. It can't be negative because it's a probability. So the important properties of this, the phi of this y and phi of minus y is same. So it is even function. It is called even function, symmetric about this x-axis. And as we go, limit y tends to plus infinity or minus infinity, it is 0. It's clear. E to the power minus infinity is 0. It's going to 0. And what is the maximum value of that? And the maximum value of that is just the max of this over y is just, this is the y is 0. So it should be y. So that means it is 1 by root 2 pi. Why this 1 by root 2 pi came? To know that, you have to integrate that total probability must be 1. So since total probability must be 1, the total area must be 1. So we have to actually integrate that integration minus infinity to infinity, that phi y must be 1. That means from 0 to infinity, because it is symmetric, the area is symmetric, that 1 by root 2 pi e to the power minus y square by 2, it must be half. And to find this, it actually needs a gamma integral. You know what is called gamma integration. Gamma integration from 0 to infinity. So gamma integration, incomplete gamma integration is not 0 to infinity, is 0 to some x. But incomplete gamma integration, you can't integrate this. You have to find numerically. But the complete gamma integral is called improper integral. That is half, and you can find that using the gamma integration. I will not go into that calculation part. I just said what is the expectation of in the continuous version. In the continuous version, expectation is in the discrete is a summation sum over x into probability of x. But here it's nothing is probability. We have to talk about the density, because in that case the sum of the probability of x equal to x is 1. Here the integration of fx is 1. So we take that fx instead of the probability of x equal to x multiplied by x and take the integration instead of the summation. This is a definition. Sometimes it's called mu x. And what is variance of x? Variance of x is it is just minus infinity to infinity x minus that mu x. That mu x is given earlier into fx dx. And it can be shown that this is nothing but minus infinity to infinity x square fx dx minus. You can easily show that using your integration property of integration. And if you just for normal distribution, if you take the normal distribution, standard or any normal, then we can using gamma integral. I just not going details in this. By using gamma integral, I am dropping this all this calculation part. I just given the result. The expectation will be mu, and the variance will be sigma square. You can find this using your gamma integration. You need some improper integral. It is not a Riemann our simple integral. This is called improper integral, gamma integral. And the finding the gamma integral is another function. Another integral is called beta. Something is called beta gamma function. So we need actually the beta function. We have to evaluate the beta function, and using beta function, we need to find the gamma function, gamma integral. So this is slightly complicated thing. So I'm not going to on that details. Just state the result. The expectation of normal mu sigma square. The expectation is mu, and variance is sigma square. And there are other continuous thing is also there, like uniform, something called rectangular. rectangular distribution, rectangular thing. Here it is just say the density function is like that, PDF is like that, it is just 1 by b minus a when once is lies between a and b. So a less than b, a b are real. So it is like just this is a very easy thing. So it is just a flat thing. This is a, this is b, the length is b minus a, and this height is 1 by b minus a. So that's why the total area is 1. So total area must be 1. And you can easily find the expectation of that, and you can check. This integration is easy. You can easily find this integration, and you will find this is a plus b by 2, and you can find the variance also, and that will be some b square minus a square by 12. I just slightly confused whether it is by 12. Yes, I think it is 12. You can easily check just whether it is b square minus a square by 12. So these are, you can easily check. This integration is very easy. This as easy as in class 11. Trivial integration. So there are other continuous distribution also, but we are not going on into that. In our syllabus, we deal with only normal and rectangular thing, and the expectation and variance. And this is the all for continuous version. We can find the mode also. Mode means mode of some distribution is just if mode is say what say m, that means your that fx is has a maximum maximum at m. That means your f dash m is 0 and the f double dash m is say negative. You know this first derivative is 0 and the second derivative is negative, means this is maximum value. So you can find mode for the normal distribution. You will get that this is just mu. That is also again easy. Just take the derivative equal to 0 and find the solution. There are several other things also, but in our syllabus only 2 things are there. So stop now here.